Okay, go ahead.
Okay, sure. Let's get started. Good afternoon, everyone. Welcome to the HAO Colloquium. So I'm taking Nick's role today because he's on a committee meeting. And today we are very happy to have Dr. Rafael Luisa Uruchi Mesquita. Sorry if that pronunciation is not perfect.
That's great, man.
Okay, thank you.
I'm impressed.
Okay, from Applied Physics Laboratory of Johns Hopkins University. Here's a brief intro of Rafael. So he was born in João Pessoa, Brazil. He graduated from his undergraduate degree in 2013 at the Federal University of Campina Grande, where he had an undergraduate research fellowship focusing on meteorite data processing and mesospheric winds research. And in June 2013, he began his PhD at the Clemson University, South Carolina. And Dr. Mesquita managed the southern instruments in the nation network of Fabry-Perot interferometers, or FPI, and worked in the lab designing of new FPIs. And in 2016, he began working in sounding rocket experiments to measure neutral wind profiles in the thermosphere, which he continued to do until his graduation in May 2021. And in July of the same year, he started as a postdoc fellow at the JHU APL, where he is currently working as a senior professional staff. And he leads a modeling study to characterize neutral wind shears globally using data simulation, and has worked in the development of rocket missions. And currently, his main task is to develop and manage the OSSE, Observing System Simulation Experiments, in support of the EZIE mission, a mission to uncover decades-old Aurora Electrojet questions. And he will be talking about the EZIE mission today. So welcome, Rafael.
Thank you for the very nice introduction, and I'm very impressed with the pronunciation of all those difficult names. Thank you very much. Yeah, so I'm very excited. Thank you, all you guys, for your time, and I'd like to thank Nick for inviting me, even though he's not here. I'm really excited to talk to you guys about this the upcoming mission, the EZIE mission, which is the Electrojet Zeeman Imaging Explorer. And full disclosure, even though I'm presenting to you guys, this is a really large team, and there would be no way that I could present to you guys today if there wasn't help from all of them. So it's a great team, and I'd like to acknowledge them here. So let me see here. All right, here we go. So I wanted to start by just giving you a very high level view of what the EZIE mission will be. So the EZIE is going to it's a mission that's going to measure the magnetic field perturbations and the magnetic field from a remote sensing platform using 3 different spacecraft. It's one of a kind, as it's the first mission that's going to probe the magnetic field on Earth with the Zeeman effect, and it takes advantage of the O2 thermal emission. And the whole point of the EZIE mission is to figure out decades-old mysteries in the Electrojet. There are Electrojet. That's the primary mission objective. All of that in the mesoscale. So we have 3 different 6U CubeSats, and they're going to have all the same instrument called a microwave electrojet magnetogram, short for MEM, and it's going to fly in the formation that you're seeing here on the right. So, going back to what the science objectives of the mission are. So, we know that there's a big chain that comes from a very complex and big chain that comes from the sun all the way to the atmosphere, and most of us have seen this image on the right. So the point here is that the spatial extraction and temporary variation of space weather and all of the varying energy inputs that come from the sun, it all leads to the Earth, and like the Earth is the anchor of this chain, right? At the end of the chain, we have the Earth. So focusing on these two phenomena, the aurora electrojet and the equatorial electrojet, primarily the aurora electrojet. So what do we know about this environment? So with measurements from ground-based networks and other instruments, we can reconstruct the spatial and temporal evolution of the aurora and the electrojet in a very large scale. So the convection patterns and like you have like things like superdorn, and you have super mag that can produce the large scale convection patterns from a ground-based platform. But the problem comes when you start to look into the morphology in the mesoscale. And to be more precise, there are several different models to explain what happens in the large scale and mesoscale. So we have a very famous substorm current wedge from McFerrin. We have the two-loop model, and we have the double edge look into it, right? So if you like draw it out into hypotheses, you can actually see the differences between one model and the other. So the hypothesis A is more of the substorm current wedge, as in one really big soup, and there's this little wiggle at the center. And then there's the double wedge model, and then you have the two loop. So the three models here, they can explain what we see from a ground-based platform, but we cannot see. We can't discern which one is the actual right. Like one of them is right, or sorry, they cannot be all right, and they could all be wrong. So we don't know yet exactly what's the case. And that's one of the main questions. So is how is the substorm current wedge configured? The second question is the aurora electrojet a large-scale current system or a set of small-scale current wedges? So the way that I like to visualize this is, like you have like either a big waterfall, or you have like a set of teeny tiny little waterfalls. Like in the picture of the McFerrin picture, or the wedgelets, right? So EZIE, with the EZIE mission, we'll be able to resolve these questions on the substorm current wedge, because we're going to be able to like measure the scale size and the temporal evolution of this electrojets in a large in a large scale of in a large number of events. So we'll be able to discern which hypothesis is correct here, or if any of them are correct. Our kind of a bonus question is related to the equatorial electrojet. So we have that the equatorial electrojet it sits plus or minus 3 degrees on the magnetic equator. So if you imagine that this is the magnetic equator here, this little dash line, you can see that like the equatorial electrojet is symmetric about the magnetic equator. But is that true all the time? Could events like the presence of gravity waves, or different phenomena, could that disturb that the symmetric behavior? So we don't know, and we're hoping to be able to respond that with EZIE. So there's a whole plethora of extra questions that we can address. And one of the big things here is that EZIE is going to measure something that's a lot closer to the Electrojet. So if you look at the swarm pass, like the magnetic field that swarm is sampling is really far from the actual Electrojet. So the signal drops out by a lot, but EZIE is going to remotely sense the splitting of an emission that is really right next to the Electrojet. So, if there is gravity waves into the data, we'll be able to see that. So, how is that the mission? How is that the measurements are going to work? So the basic principle here is that we are going to use the Zeeman effect. It's many years of the Zeeman effect is very well understood. So you have an emission that's centered right here, right? But when you apply a magnetic field, the emission, the spin of the emission, it splits because of the response to the spin, right? So we're taking advantage of that, and that's a thing that has been used for many years. So this is an observation from 1908 of a sunspot, and you have a spectrometer here, and you can see that outside of the sunspot, you have that really nice line where there's absolutely almost no spreading of the emission. But when you get to the sunspot, where the magnetic field is supposedly a lot higher, a lot larger, there is this little spread. It's hard to see, but there's one pi line right in the middle, and there's two sigma lines on the sides, right? And from that initial observation, we have evolved to much more intricate measurements of magnetic fields on the sun, as you can see here on this highly structured, solar active around the sunspot. So, has this ever been used on Earth? So, yes, but no. So we have this in the on board of the Aura, the MLS, the limb sounder instrument. It takes measurements of limb, and it uses the O2 118 gigahertz emission of the oxygen, right? It's a thermal emission. It's always there. It's very uniform. It's very nice and sharp at about 80 kilometers, 90 kilometers. And when you look at that emission, you can see that the proof of concept is here. So you see that at the equator, where the magnetic field is a little weaker, you have the separation between the two peaks is very small. But when you start getting to higher latitude, the separation becomes higher, and that's correlated with the magnetic field, with the scalar magnetic field here. So basically, this separation between these two peaks here are basically directly proportional to the magnetic field, right? Now, I'm going to show you guys later how we can actually get the vectorial measurements from this. The MLS only measures routinely one polarization. So here in a minute, I'm gonna talk more about how these polarizations affect the angles between the polarization and the magnetic field that affect how we measure. So what are the advantages of the easy way of probing the magnetic field? So far we have measurements of satellites, the magnetometers, ground magnetometers, and sounding rockets. We have measurements of the of the electrojets, and we've had measurements of the magnetic field perturbations with these 3 types of platforms. But they have like really critical disadvantages. So the rockets are very short-lived. You can only, the rockets is flying about a kilometer per second. It's going to cut the electrojet region very quickly, and it's going to fall, and that's it. You're done, right? The magnetometers from the ground or from a space platform, they're both very far away from the source of the electrojet, which is in the E region, around 110 kilometers, 125 kilometers, right? Now, the remote sensing measurements with EZIE is never been done here on our field and on Earth. So the advantages is that it uses a remote spectrometer that's based on the Zeeman splitting of the O2 thermal emissions, and that emission peaks at about 80 kilometers. So 80 kilometers plus or minus 80 kilometers with a 10-kilometer full width half maximum. So at the end of the day, you have an emission that's being split literally right next to where the electrojet is happening. So the decay of the magnetic field perturbation is going to be very, very small between the electrojet and the 80 kilometers. We are going to have multiple spacecraft, and that's going to be able to give us an idea of what the temporal and spatial resolution is going to be for the configuration of the electrojet. And that's yet another new thing that we haven't done yet. We have that one single spacecraft will have like 4 different look angles. So it's going to look at all times at 4 different locations, basically at 4 different angles. And it's not like alternating between them. It's like always measuring them. So we will have like a 3-second resolution of this emission. And each of these yellow beams will have a magnetic field measurement along the trajectory of the spacecraft. So one of the big advantages of this method, aside from the stuff that I've already told you, is that it's way cheaper. Just imagine that, like the 3 spacecraft from EZIE, if we had to introduce in situ magnetometers to cover the same, the same type of measurement that EZIE will be able to give, we would need 12 spacecraft when we only need 3. So it makes it so the mission is a lot cheaper, and it puts us in a category of mission of opportunity. So when will we measure and where? So the primary science objective is our Electrojet, and we're going to have a polar orbit that we have a calibration phase, and the science is going to be across the polar cap, right? So you can see that the purple there is the purple lines there are the science view, the views, and the yellow is a calibration that we point up to space, right? So this is during the northern summer and southern summer, but we also have that bonus question of the equatorial Electrojet. During the equinox, we'll have multiple passes on the equatorial Electrojet around the equinox period, right? So, as I said, like the polar orbit, it's the instrument is flying in the spacecraft that are in a polar orbit, and it starts by pulling pointing up and has a calibration phase, a code calibration, and then it starts the science measurements. It's a circular orbit at 525 minima, and it's sun-synchronous, so it's always measuring close to the midnight. And we have that our launch date is going to be between late 24 and early 25. We're still working on the schedule for the windows. So as you can see, one satellite is followed by the next. So the first satellite is going to measure. The second satellite is going to go 2 minutes behind that. The third satellite, the nominal observation is 8 minutes behind the second satellite. So between the front satellite and the last one, and the back satellite, EZIE, we're going to have a span of 10 minutes. And that's our science, our science, primary science objective and the calibration mode. So the cool thing about EZIE is that, even though we're just pointing on the direction, like you would think that like we'd be able to only measure the magnetic field along the line of sight as, like a projection of the magnetic field onto the line of sight. And that's not really 100% true, because the EZIE emission, the EZIE splitting of the O2 is polarized. It can be like split into different polarizations, right? So as I showed before, the magnitude of the magnetic field is it's directly proportional to that separation, right? But the thing is, the direction affects the direction of the magnetic field, and the polarization, the direction of the magnetic field affect the different polarizations in a different way. So you have that the red curve here is the vertical linear polarization. The blue is the horizontal linear polarization. And we have black and green as the Stokes 3 and 4. So you can see as we change the different directions of the magnetic field and the strength, that it affects these polarizations in a different way. So you can actually measure the different magnetic field components at all times during in the line of sight, which is amazing. And we can, I don't talk too much about this, but for example, if at any given point we decide that 2 minutes is too high of a separation for seeing the differences in the Electrojet, we can use differential drag in the spacecraft to bring them together, to bring them closer together. For example, spacecraft A is going to turn its face that has the highest drag forward, and spacecraft B will catch up a little bit with spacecraft A, or vice versa, and that's just incredible. So there will be different, there will be additional products. So we set out to measure just the magnetic field, and that's our primary science objective. But everything everything that we do is subjected to Doppler shift. So, for example, if we have an atmosphere, just imagine a hypothetical atmosphere that is moving away from the spacecraft as we measure. So that would be one of the spectra, right? Like the black line there is the vertical linear polarization spectra of the nadir beam, right? It's the beam that's pointing straight down. Sorry, the beam that's pointing like 45 degrees. That's the beam 0. Imagine that we have a perfectly uniform neutral wind that's moving away from the spacecraft. What that's going to do is it's going to shift the entire spectra a little bit to the left, to the right. And, we have that, we have an internal local oscillator that's going to give us a reference, but also we have a nadir beam that points down at all times, and we're going to have a 0 meters per second wind reference with that beam. We're also going to be able to measure temperature profiles. So just imagine that we're going to measure the spectra that's shown in black at the top, right? But the thing with that spectra is it is a integration of what we see along the line of sight. It's the radiative transfer along the line of sight, right? And with a little bit of basic knowledge of how to come up with the radiative transfer equations, which we do have, you can come up with the contribution function on, or what that means is where each Kelvin in brightness temperature is coming from, right? So for example, in the wings here, the temperature is about, 240, 230 something Kelvin. That's actually the temperature around 50 kilometers, right? And as we get closer to the center here, the lowest part there is where the mesosphere is the coldest. So it's about 216. So we actually have like an altitude information of the temperature, right? And we'll be able to get that with like a really high precision. So how do we know this? And that's kind of the part where I started here at APL and in the EZIE mission. So we know this based on this thing called an observing system simulation experiment, which is called the OSSI. So, like lots of folks are very familiar with OSSIs. They're usually just like a sampling exercise. For example, you have like you're trying to measure the wind, and you know that the line of sight is like this. And you have like a model like Wacom X, and then you just like project the line of sight onto that. We project Wacom X onto that line of sight, and then you integrate in some way, by weighing it with the 630 emission or the 5577 emission or something like that. And then you just integrate that, but you're not really like simulating what the spacecraft is going to be, not really inputting the system into the equation. So the EZIE OSSI is different. Like we are very careful to simulate the actual system. So we simulate the brightness temperature, the different polarizations, the brightness temperature profiles, like the little spectra right there. And then we have a way to measure what the realistic noise for the spacecraft instrument is going to be in the lab. So we've done that, and we can actually include that noise into this simulated measurements. And then with that simulated measurement, we can retrieve magnetic fields with error. So like the little lines there, green, yellow, blue, and red, are actually the same lines as this thing here, as this picture of the equatorial of the Electrojet here, the Aurora Electrojet. So it starts with a global MHD model, which is, we use Gamera for that. And then we simulate what the measurement's going to be. We include the noise, and then we retrieve the magnetic fields as you would from the measurement. And then you reconstruct the currents, which, it's remarkably the same, right? So the steps, the different steps of the mission that this experiment has helped us, it comes in play when we're optimizing the mission design. For example, like the spacecraft separation, the orbit that we're going to use. We mature mission operations. For example, we validate the pipeline, and we figure out if the science is actually closing. Excuse me, I need some water. Okay, yeah. So and then we use it to establish system requirements. For example, we include every single source of noise and error to the measurements, and we come up with like baselines for what those errors and noise levels will be, so the mission is still successful. And then we test and ready retrieval algorithms for the magnetic field. So like by the time that the satellite flies, we're going to have an entire pipeline already made with very realistic data for this particular mission. And then we demonstrate the measurement capabilities. For example, we do get runs of Gamera that show the different models that, the different ways of explaining the Electrojet, as I showed before. And then we pass through those morphologies, and we get to show to the reviewers and the community that we can actually do this. We can actually measure. We can actually prove that we can measure, right? And of course, we can ensure science closure. So this figure on the right here is basically the gist of what this OSSI data flow looks like. So when you have, by the time that we have the mission, we're going to have like somebody is going to collect the raw telemetry, like, the instrument's going to collect the raw telemetry, right? Like the basic telemetry for the mission. And then that's going to be transformed into L0 data, which is geolocated on calibrated instrument counts. And then that's going to get calibrated into brightness temperature. And there's going to be another procedure to calculate the geolocated magnetic fields. And magnetic field perturbations will be lumped in here. And then there's going to be a procedure to transform that into our Electrojet currents, right? But the mission is not flying, so we use the OSSI as a way to build this pipeline. So the OSSI takes a bunch of inputs, the orbit, the global MHD, the atmospheric models, and it would build the simulated brightness temperature. We convolute that brightness temperature with real spacecraft, real expected values for the errors and the jitter, and like the different temperatures for the sensors and things like that nature. And we do the magnetic field retrieval, which is the same as the L1 to L2 here, and the Aurora Electrojet's current retrieval. So excuse me. So the mission is not flying until 2025, but we already have a tool in place to like actually retrieve the magnetic fields, which is kind of nice. So for you guys to take get a sense to what that means. So at the left side here, the leftmost plot is the convoluted radiances. So this is the different polarizations that we're going to measure, and you can see that they're kind of shimmery, like there's a little bit of noise there. That is very realistic noise from the instrument, right? Like if we look at the instrument, and if you look in the lab, the amount of noise that we expect from each for each of these polarizations, we know that it's going to be in this more or less in this level of noise, right? So from here we calculate the sensitivity, which is basically a Jacobian transformation from Kelvin to nanotesla. And then we apply that to the convoluted radiances, and then we have like the red lines that you see here, which is the magnetic field measurements, right? Just the perturbations, like the background field from IGRF is extracted from it. So you can see that it's a remarkable, it's a very remarkable measurement, right? So it's very close to the magnetic field. the dashed blue line, which is the at 80 kilometers from Gamera. And at the bottom here, we have the reconstructed currents. So like this is the current from Gamera and the reconstructed currents from our measurements, right? So one more example here on the EZIE. So this is how we establish the system noise requirement. For example, if like we know that to be able to respond to the science questions, we need the error, the 1 sigma error of the mission. It needs to be in the order of 200 nanotesla or less, right? So I picked this one flight of the mission here. So like that 9-minute, like this 9-minute window here is where we're measuring for this particular pass. And that 9-minute pass is has a 3-second resolution with the spectra. Each band of the spectra is 100 kilohertz, right? And the measurements are what you see here in red, right? So you have the little red measurements right there. So once you have the measurements in red, like if you do like a little basic analysis of what the error distribution is going to be, I just compare the red line with the blue line and create a distribution of that, the deviation from the truth. At the best estimate of the instrument is going to be an error of about 33 nanotesla, which is crazy. It's extremely good. So what else can we tell about the atmosphere? So for example, here is a very preliminary temperature result that we have. So at the left side here, you have like the more physical, not the Stokes polarizations. You just have a vertical linear, horizontal linear, right 45 linear, left 45 linear, and the left circular, right circular, right? But focusing just on the top one, on the top two, along that thin, very thin line there, right? So at about 2.5 megahertz here to the right, you have that this measurements coming from approximately, let's say 50 kilometers, right? So that is the temperature at around 50 kilometers. So if I plot the data along this little line here for the vertical and the horizontal linear polarizations, you see the orange and the blue lines here. So like you see that they're basically like right on top of each other. There's almost no difference whatsoever. So there is a interhemisphere difference, maybe about 10 Kelvin from the southern hemisphere to the northern hemisphere. This is a northern hemisphere summer, right? And what I did was I just put like a simple pass band filter, like high pass filter, right? And I calculated the, like this oscillation here. So it's about like, 0.2 Kelvin, which is like, you might say, nah, this is nothing. This is absolutely nothing. But if you propagate that into the mesosphere, with the scale height into the mesosphere, that actually is comparable to a lot of the gravity waves that we measure in the mesosphere. So this is really exciting for us to be able to delve into this world here. So the same can be done with the winds. So I basically just did, like at 80 kilometers, using one of the beams from EZIE, the line of sight when at that beam, based on the shift here that you see, that's like not really symmetrical. The spectra is not symmetrical. So based on that shift, that blue line is what you get. That would be like a Gaussian mean at 80 kilometers, right? And Wacom X at 80 kilometers is that red line for this particular pass here, right? So when I do again the high pass filter for that, it's about a 2 meter per second, like peak to peak is about 4 to 5 meters per second. And we'll be able to measure this with really, really good precision, because this is accounting just one spectral bin, right? We have like, like this here is like about 7 megahertz from end to end. And each spectral bin is about 100 kilohertz. So we have a lot of data that we can use here. I'm doing good on time, right?
Yes, we still have 20 minutes, so no worries.
All right. Cool. All right. Thank you. All right. So what can we do with the wind? So because we do have the Aussies, because we do have like what preliminary, what it's going to be measured. So we get here, just using the line of sight winds, right, along that little lines. So we can reconstruct the wind field in the mesosphere with the spherical elementary current systems procedure, right? Just basically assuming that things are divergence free, and it fits. It does a fitting for the spherical elementary current system. So when you compare that with Wacom X, it gives a remarkable the difference between this field and this field, which is straight out of Wacom X, it's this field right here. So like inside the 4 beams, we're gonna have like really good measurement of the winds by just using the line of sight winds, which is amazing. So at this point, I wanted to like change gears a little bit and talk about different collaboration opportunities that you guys could potentially want to jump in or like join us in the effort. Like there are a couple of things here that I wanted to mention. So the number one thing is EZIE Mag. So what is EZIE Mag? EZIE Mag is a citizen science initiative that's attached to our mission. So one of the people here at APL, they created this little low-cost magnetometers. Costs about $100, right? So it's really good for this price point, right? And the whole idea is to make a network with about 100,000 of them, just spread out into like high schools or universities, like things that the students can actually be hands-on with, right? And really, like the goal of it is to just develop this very practical. You can fit it in a Pelican case. I wish I had one here. I don't. We can fill it in the little like 1060 Pelican case. I'll show a picture here in a second. So it uses like this really low cost magnetometer chip that it gives remarkable results. So here is our prototype kit. And, like I'm not going to bore you guys with the details on what's made out of or whatever. But this is our prototype kit. This is our testing unit that we have right now. And it's deployed in one of our guys' backyard. It has like 3 different ongoing tests with it. He's got like a $20,000 really good science magnetometer. And he's got 3 of these little units in different conditions, like covered, just in the sun, like sun at all times. And, like in a styrofoam box, right? Excuse me. So each of these units, it'll be, Wi-Fi enabled. So you essentially like put like a 20-foot cable, throw it in your backyard, and forget about it. It's gonna have a temperature sensor. It's gonna have an accelerometer, and it's gonna have a GPS sensor, right? So it operates by itself. Like all you have to do is to put like your Wi-Fi information in it and plug it in and just chuck it in your backyard, right? It doesn't care like what orientation is. It does that for you. It knows what's up and down, and it does the orientation of the field for you. And he also does the temperature calibration, which is amazing. So the idea is to have like lots of these little guys, and we are in the process of actually making EZIE Science Gateway, which is going to enable the students to actually like go into the EZIE website and say like, all right, this is my magnetometer, this is how it's working. And then like if the student actually grab the magnetometer and like flip it upside down or whatever, he's going to see the differences in the data and things like that. It's going to be something that's it's something that's designed to get students excited. Okay, yeah. So we're planning to have like distance between two units to be about 100 kilometers, and the data from this thing is going to be it's just like it's just remarkable. Like for example, if you look at the red line here, that is Fredericksburg. It's a USGS magnetometer that's about 100 kilometers, maybe less. 100, like 90 kilometers or so away from where the black line magnetometer is. And that is already temperature calibrated. It's got the correct like field rotations and everything. And you can see that like even the littlest bump in the magnetic field is well represented there, right? And just to be clear, these are magnetometers that are standing like 100 kilometers apart, right? And the good news is the black line here only costs you about $100. Like one of the most expensive things is the actual Pelican case that holds it. So, you can even skimp on that if you feel like it. So all of this is going to be like open source. Like if you guys are like trying to collaborate, and if you want to have one of these, if you want to make your own, we can share the plans with you. Like there's absolutely no closure here. There's no like, we want to have as many people as possible, right? And we have like 5 different packages and tasks attached to this particular project. One is the hardware. We're already in the 3rd generation of this hardware. We have the software for operating the hardware, which is in 2nd generation. We also have the rotation and calibration of the data, which is 2nd generation. We already have a website. It's pretty plain. It's functional, but it's very, very simple. And the outreach material is being developed right now. So like we have like little movies, and we're going to have like a manual on how to put the magnetometer together. That's going to go to all the high schools and, like middle schools that we're going to ship this stuff to. Right now, we are starting the beta test, which is going to be a large-scale test that's about 100 units. It's going to be, I've seen the first few units, and it looks absolutely awesome. Like, like that black plate that had in the background is now like gold, and it's got like all kinds of cool stuff in it. And you just like point to where like everything needs to be connected. It's awesome. And a message for you guys is that we are looking for participants in different geographic sectors to evaluate the kit once we have, like the full units, right? And like probably even now, like in the beta test phase, like it would be beneficial for us to actually have one where you guys are. So reach out to me if you're interested in it. Like I can get you in the newsletter for it. I can get you the newsletter set up, and we can start communicating here. So the second opportunity is the EZIE Science Working Group. So like, as I showed you guys, like we have like multiple, we have a lot of already ongoing, like already working algorithms, right? Like we already have an algorithm to retrieve the occurrence. We already have an algorithm to like transform the line of sight winds into horizontal winds in a field. Like we have a lot going on. So these all take place in the science working groups. So I have two examples here: the Equatorial Electrojet Science Working Group and the NeutroWinds Neutrodynamic Working Group, right? So these are just two, but we have several different working groups. So if you're interested in participating in these, all you have to do is to just like send me and Jesper an email. Like I'm gonna have Jesper's email at the end of the presentation, so you can communicate, and like we're more than happy to have you. Like our lemma is like if you want to work with us, we want to work with you. So even if just to like know how to use the data once the spacecraft is flying, if it's just for that, it's a good idea to participate and like come and like give your opinion on the subject, and we're more than happy to work with any of you. One good thing that I can announce now is that we are going to have our first EZIE Science workshop. It's going to be held in Monday, September 18th to Tuesday, September 19th. It's going to be both in person and hybrid, so you can make your way up here to Maryland to like watch the talks and have a conversation with us. Maybe see Maryland and stuff. And the registration is open now. It's in the EZIE website. I put like a little QR code here in case you guys want to participate. I know that this is being recorded, so like you can always go back to that and check it out. So in summary, I think I'm getting there. So in summary, we have a really, really exciting mission with really good potential for collaboration. We really want you, the community, to participate, right? We're hoping to be able to answer like this conundrum of questions that had not been responded for like ages. And we hope that you consider like joining our team. So where we are right now in the schedule is we just gone through CDR, is the critical design review for the mission, and we passed, so we're good. Like NASA gave us a little gold star. We're chugging along to the launch opportunity, right? And lastly, I have some basic information here on the mission, and there's some reading materials. There's the science workshop. There's the EZIE website, which is a really cool website. I would encourage you guys to take a look at it. And there's some, like EZIE on a glance is like a 3-page PDF that you can like get a summary of what the mission is. And the EZIE Mag website that you can get the newsletter. And these is Sam Ye is the PI for the mission, so you can email him, and you can email Jesper, who is the project scientist, or you can email me, and I'm happy to help you guys out on getting in the team. So I hope I didn't speak too much, and that's all I got. Thank you guys for your time.
Okay, thank you, Rafael. Let's give a round of applause. Yeah, by the way, I put the EZIE website in the chat. You can check out if you haven't got a chance, ezie.ghba.eu. We still have a few minutes for discussion. So anyone has question, please hands up, or just okay, Samaya, is that you? Oh, hands down. Samaya, oh, are you still here? It looks like, well, yeah, you can go ahead if you have a question, or other people can hands up. Okay, Fabrizio, please.
Yes, hi, nice talk.
Thank you.
A bunch of questions.
Uh-oh.
No, these are good questions. It's curiosity. So you, in one of your slides, you had that your signal peaks at 80 kilometers. So what's the range of altitude so that you can cover? So effectively, I'm curious how high you can go. And also laterally, latitudinally, you mentioned the equatorial electrojet. I'm assuming that the signal is much weaker towards the equator, and so how you're going to deal with that.
Yes.
And then the final, I'm going to give you all the questions, and then you can decide how to answer. And then the last question is, don't you need also, for your reverse modeling, don't you need an NWP, a numerical weather prediction model that will tell you if there's a thunderstorms and you see some perturbation in your B field, something that guides you the interpretation of your observations?
These are very good questions. Thank you very much. So I'll start with the last one. The thunderstorm one is something that we actually hoped that we could see, but the magnetic field perturbation from a lightning and from a thunderstorm in the mesosphere is going to be very, very small. So it's an order of magnitude, maybe a few orders of magnitude smaller than what we're showing here. So it's going to be really hard to discern what the, like the separation is going to be if it's related to that little itty bitty, like, half a, like a, maybe like a couple hundred kilohertz separation because of that. And the, like normal atmospheric fluctuations, right? The second question was, do we need to, sorry, can you repeat the second question again?
The second question was about the need for a numerical weather prediction model, whether you need something to guide the interpretation of your observations. I mean, you're using now an OSI system.
Right.
When you're operational and you're taking observations, don't you need also something to tell you the background conditions and things like that?
No, because the below 40 kilometers, the emission is just very thick. It doesn't like the radiative transfer. It basically, like, all you see down is down to about 40 kilometers, right? And also this emission peaks at 80 kilometers, and it's got like about 5 kilometers thickness to it. So it's like a kind of a sharp emission, right? And yes, in the equatorial region, I remember the first question. In the equatorial region, we are going to have we're going to have a harder time measuring the equatorial electrojet because, one, it's a lot smaller, but more importantly, because two, with the satellite pointing straight down, you're essentially pointing perpendicular to the magnetic field, right? And the sensitivity to this here, you can see that, like, like as the arrow is changing there, like the emissions at some point you just get like a flat emission at a peak at the center, and like all the others are very flat and small, right? So that's a kind of a convoluted way to say that because we are looking straight down perpendicular to the magnetic field, just about, it's a lot harder. So looking parallel to the magnetic field, which is good in the high latitude region, gives us great noise. Great, like it's really low noise, but in the equatorial region is really hard. But we are working in like different fronts on how to improve that. We have come up with like 3 different models to like retrieve the currents. Let me see if I can show you something here. So when we are trying to retrieve the currents here, like this, pointing to my screen here. Anyway, so like when you try to actually like go from this here to this, you have that along that line, you have like little noisy, magnetic fields, right? But we use all 4 of all 4 lines. Like we use the magnetic field on all 4 beams here. to actually retrieve the magnetic field. So like it creates like the best fit for it, and like the noise levels, it kind of beats the noise levels, which is amazing. So again, to respond to your question, it's going to be harder on the equatorial Electrojet, yes, but we have some strategies that we are working on to, make it better.
Thank you. I don't want to take the time from other people, so thank you very much.
Sorry.
Okay, thank you both. Let's have one last quick question, if anyone. If not, I have a quick follow-up about the equatorial measurement. Can you just like tilt the sensors when you are at the equator so that you got some angle?
That is definitely one of the strategies. So for example, like we have like all kinds of cool strategies for this. Like we can, for example, we have two spacecraft like this, right? We figure out that like if we do this, like 5 degrees on this one and 5 degrees on this one, we can retrieve the neutral winds with a lot higher precision. That's one way. If we do like, instead of like doing straight down like that, like, like against my jacket here, instead of doing straight down, we do like a little like that. We're going to get a lot better signal on the equatorial Electrojet. So like, these are all like things that we are currently working on, right? So it's all things that we can do, and we are doing, the analysis that needs to be done for proving that we can.
Okay, great, thank you. I think it's probably time, and some people may have to go to their next meeting. Just remind again the EZIE workshop, but I just found the link seemed to be not working when I click on the website, so you may double check that one. Okay, thanks everyone for coming. Thank you, Rafael, and hope to see you next week.
Thank you so much.
Yep.
Good seeing you guys.
Yeah, good to see you. Bye, everyone.